What is the most used man-made material on Earth? You guessed right. It's concrete. Look around. It's everywhere. Sidewalks, driveways, foundations, floors you stand on, and even entire buildings are made out of concrete. So why don't we discuss it more? In each episode of Concrete Logic, we will explore one concrete-related topic with the help from industry professionals that are shaping the future of the trade. We'll talk with suppliers, contractors, architects, engineers, specialists, and even some proponents of competing materials about their views of concrete and their vision of its future. Welcome to another episode of the Concrete Logic podcast, and Dr. Jon Belkowitz is back with us. It should be this is number eight. Number 8. All right, so we're going to talk about colloidal silica today. We haven't talked about that in a while, so I thought we would rehash that. And plus, it makes Dr. Belkowitz happy to talk about it, so that's why we're choosing that today.
You know what else makes me happy to talk about?
What?
The t-shirts. And I just wanted an update on the t-shirts.
All right, well, I'll give you an update. Nothing's happened. Nothing's happened. So before we spend time talking about t-shirts, I just want to remind everyone how this works. The podcast. So I bring folks on like Dr. Belkowitz and give you a bunch of knowledge for free. Just throw it out there. And what I ask for you in return is to do 3 things for me. You can do one of the 3 things, but just do one of them, please. One is share the podcast with a colleague or coworker in the industry or even outside the industry. Get somebody that's outside the industry, get them involved in concrete. The second thing you could do is you go to concretelogicpodcast.com, and there's 2 ways to get a hold of me. There's a contact link. It's up at the top. I'm on the website right now. It says contact. Click on that. You can shoot me a message, and you can do what Dr. Belkowitz did for me this morning. Give me a guest suggestion. He gave me a guest suggestion who I reached out to, or a topic suggestion. Either one. So that way that we make these episodes about what you want to hear about and not just what I want to talk about. And then the last thing is if you find there's value in this show, you can show your give value back in a monetary way by hitting the donate button that's on the website as well. So click donate, and then you can give any amount, and any amount is muchly appreciated. It's just your way of showing that you're listening and you're learning something from the show. So with that, we can talk about t-shirts real quick if you want to. I've done nothing with the t-shirts.
No interest in talking about t-shirts. Bro.
Okay. Eventually there'll be a some kind of t-shirt. We'll figure it out at some point. But it's been a busy part of the year, you know. It's summertime. It's the season of concrete, so it's been busy.
Right.
Yeah. So, but colloidal silica. Let's talk about that, and maybe you should start off by reminding folks what it is, and what we use it for, or what it can do. I know it's a favorite subject of yours.
Oh, absolutely. And, you know, a good definition of colloidal silica, we have one written up in our ASTM, which is part of our discussion here. Do you mind if I open it up real quick?
No, that'd be great.
You know, and just to give you a background on colloidal silica, the history of it, it's been around since the 1800s. And, you know, I think the first patent for it was back in 1959. And the person that I attributed to it, there are a bunch of other folks out there that like to give other people credit for it. You know, I'd like to give Brian Green from the U.S. Army Corps of Engineers the credit for bringing colloidal silica not only to ground and mortars, but also to the concrete construction industry with his work on ultrafine amorphous colloidal silica for rock matching grouts. Great research paper. If you've never read it, it reads like Mark Twain, or Call Me Ishmael, which wasn't by Mark Twain. Anyway, so a definition for colloidal silica, which you also might find it in the literature as silica sols, is a controlled suspension of nanosilica-sized particles anywhere below 1 micron, because that effectively is in the nano realm, but normally it's considered between 1 and 100 nanometers in the concrete industry. And there are others that will push it up to 150 nanometers in diameter. Just to give you a reference, human hair, not on your head or my head, but human hair has a diameter of around 100,000 to 150,000 nanometers in diameter. So a nanoparticle that we're talking about, this nanosilica, can be anywhere between 1 and around 100 nanometers in diameter. Just a little bit bigger than a water molecule, if you will, and a little bit larger than that. And the reason why we like it is because these ultrafine amorphous particles in suspension, which are not affected by gravity, they react well not only with concrete and things like pozzolanic reaction, but then you get particle-particle packing, you get void filling, and then you get things on the chemistry side of it like accelerated cement dissolution or instantaneous pozzolanic reaction or internal curing from a hydrogel creation. Now, it should be noted that there is a separation between colloidal silica and the raw material that's used to make colloidal silica, which is considered to be a silicate. Now, the first thing, I guess, is the pH. When you look at a colloidal silica, they are below a pH of 10.8. Anytime we hit a pH of 10.8 with colloidal silica, what you start seeing is this dissolution or this dissolving of the solid species. And once we hit that pH of 10.8, you don't have those nanoparticles in solution. Now you have solutes in solution. So it's really the pH, which colloidal silica can't be above really 10.7. Once we hit 10.8, you're a silicate. And also it's the size of the particle too. Silicates are solutes in solution, as opposed to colloidal silicas are discrete particles in a suspension.
So at that point, you would lose the, I guess, the beneficial attributes of silica, right? Or what would a silica?
Yeah, so it's the benefits to a certain degree are similar, but it's really the fact that it's a lot harder to control the silicates. Let's say when you're using them as a densifier. Silicates have traditionally been used in the concrete industry for the last, 4 or 5 decades as concrete densifiers. Top surface, topical admixtures. And man, oh Shevitz, are they great? Far be it for me to say silicates aren't a good technology for concrete. I freaking love silicates, especially when you start combining the different types. But there is a specific use for them, and the unfortunate reality is that people don't often use them in the right places. Now, using it as a densifier, if you're polishing, it works great because it's so reactive. And that's the thing, it's a solute in solution. It's very, very small. There's a lot of salt with it. So it will react pretty darn quick. That means we're not going to get the depth of penetration if we want to impact the concrete through the surface, into the subsurface, into the body of the concrete, like we can do with topically applied colloidal silica. Again, much larger particles that don't react as quickly. Oftentimes, when you're using a silicate densifier versus a colloidal silica, if you have the same concrete, you separate it with a piece of tape, silicate on the left, colloidal silica on the right, what you'll see is the colloidal silica, when you apply it topically, it looks like it's drying faster,
Mm.
right? When you look at the silicate, it looks like it's pooling and ponding on the surface. With the silica, it's just uh, absorbing or dispersing or diffusing into the concrete. You're not seeing it dry, you're seeing it dive into the concrete. With the silicate, it reacts so dang quick that it creates a boundary layer or a gel that prohibits more of that solution to penetrate into the concrete. So you are effectively pooling or ponding on the surface. There's a concrete polishing guy out there. He reminds me of what's it called? A band from the 80s. I think his company is called Extreme Polish. He has another great guy for you to have on the podcast. He's got some awesome videos where he does the comparison, and he literally does what I just said, and you can see the difference between silicate and silica, and you'll see almost like a glassy surface. That's because the silicate is gelling at the surface. It's reacting really quickly. Now, you can mechanically use that and what's it called? Finish it into the surface, if you will. But again, it can only penetrate so deep, and therefore it only has such penetrate or has such a impact. The other problem with silicates is, bear in mind, you have a lot of salt for one SiO3, right? Somewhere on my computer, I have a wonderful presentation, and I can send it to you, and you'll have some great pictures to put on the podcast. That salt content, usually in the form of sodium or potassium, can cause issues for concrete, especially, sorry about that, especially if we're using the concrete floor for, let's say, a resilient flooring, an adhesive with a rollout tile or vinyl tile floor, rubber flooring.
Applied flooring, you're saying.
Right. You did a podcast with the great Robert Higgins.
Yes.
You've got to read his last two articles.
I read everything he puts out.
There was one, I think it was the second to last one, was on sodium content in the concrete and how it drives moisture content. I would love to work with Robert on an article about the hydrolysis of adhesives in the flooring industry, because a lot of these potassiums and sodiums in combination with moisture will cause a breakdown of the adhesive, and then you see that delamination. It's called hydrolysis. A lot of folks incorrectly call it reemulsification. And basically what's going on is you have this overabundance of salts. The pH increases. Of course, you have the moisture that goes with it. It's an environment that is not conducive to the life cycle of the adhesive. And then there's either whether an electron donator, an electron acceptor. I've got to do more research into hydrolysis. That's why I want to write this article with Robert. But basically, you break down the glue, and we have all these issues. If you look at, I believe it's ASTM F310, it's either 710 or 3101. It's the flooring ones for resilient flooring and a coated floor. I want to say that it's within the top two paragraphs that it says that you have to remove all reactive compounds, and you cannot use reactive compounds on the surface. I believe there's also, if you look at ASTM 309 and 1315, I know for a fact in those paragraphs, it stipulates that they have to be non-reactive compounds with the surface. And as it turns out, over the years, there have been a lot of companies that have been selling silicates in the guise of colloidal silicas, and it doesn't take a very long Google search to find out some of these companies, but they were selling the silicates as a way for contractors to reduce the amount of time to put their flooring system on, right? And I don't know if Baker did any concrete or hospitals with vinyl tiles or schools or anything, but some of your contractors might have been introduced to this topical additive that, hey, put this topical additive on, and instead of waiting, 30 days for every 1 inch of concrete, now you can put your flooring on in 7 days. And don't worry, you don't have to test your concrete. Trust us, it works. Now, that works short term, but long term, and I encourage everybody to read Robert Higgins' article. With the amount of sodium that you're putting on the surface, you're eventually going to draw moisture. And that combination increases the pH and problems ensue. So short term, the silicates were what seemed like a great opportunity to reduce the critical path. But what we're finding now is those jobs done in 2014 through 2017, they're causing some issues.
Yeah.
Now, I like the idea of using a silicate in areas where we have soft water, where we have acid attack, like manure pads, manure basins. Like, how awesome is it to use a silicate in a manure basin where you have a pH of 2.4 to 3.2? Thank you for choosing this topic. I'm in such a good mood, Seth. This was a much better idea. I really do appreciate that. Again, so have you ever studied acid attack on concrete, Seth?
No. Sounds interesting.
Whitney wrote, bless Whitney's heart, she wrote a paper years ago. I believe she was doing a project at not Idaho, North Dakota, University of North Dakota, with Professor Daba Gaddafa. And they did this whole research on acid attack of concrete with colloidal silica. And we were doing it for a couple of mining companies, or they were doing it for a couple of mining companies, or sponsored by. And what we found is that once you hit a pH of 2.4 to 3.2, something has to be sacrificed to raise the pH. Otherwise, the calcium silicate hydrate structure will start to give out electrons or start to break down to balance that pH or raise that pH to neutrality. Because remember, that pH always wants to go back to neutral. If there is not something there that can raise the pH, the concrete surface will sacrifice itself. And when I say the concrete surface, I want to be specific. That's the hydrated cement matrix, the calcium silicate hydrate. pH is lower for stronger calcium silicate hydrate, the type 2 or the inner product. The pH is closer to 3.2 for the weaker or type 1 calcium silicate hydrate, or the outer product that isn't as dense, right? If you use, check this out, right? If you use just standard concrete, right? Let's do a type 1-2, a water cementitious ratio, or a type 1L, I guess nowadays. 1250 on the rock, 1750 on the sand. No freaking water reducer, no air entraining admixture, a water cementitious ratio of 0.45, and we'll say a total cement content of 564 pounds, right? And you use this for some type of poop basin, a manure basin, agricultural basin, even a shit tank, for a clarifier. Your pore water solution of the concrete will have a pH of what, Seth? Give me a guess.
I have no idea.
Somewhere between, let's just say, 9 and 11.
Oh, wow.
Right. Well, I mean, the pH of standard concrete is somewhere around 10 to 11, right? Let's look it up. What does Wikipedia say? pH of standard concrete. Okay, sorry. Freshly poured concrete is 12 to 13, and then it reduces after that, right? Now it reduces because we're starting to go through some chemical reactions and we're converting the alkalis and hydroxides into nanogels called calcium silicate hydrate. So the pore water solution, the pH dissolves, or I'm sorry, lowers. If we use a sodium or potassium silicate, whether it's a topical solution or my favorite way of doing it is an integral admixture for concrete that is meant to be used for, let's say, manure basins, we're creating an environment where we're going to effectively have more salt in our pore water solution. So that means our pore water, our pore water solution will act as that buffer solution to drive down that pH. So the pore water is the sacrificial, not the calcium silicate hydrate. And dang it, if that's not a good idea. The same thing with soft water attack. It's the same freaking principle. Oh gosh. And I tell you, I've seen more companies sell silicates to concrete polishing companies, which, hey, that's a great idea, or schools, hospitals, other freaking flooring companies that are going to be putting a resilient flooring system down. And then the contractor doesn't do a good job and, refer to Robert Higgins' paper and your adhesive breaks down.
Mm-hmm. But let's get back to silicas.
So let's go back to the same scenario. You look at most silicas, colloidal silica, I love the way Brian Greene writes it, ultrafine amorphous colloidal silica, right? Like it's like poetry. pH is much lower. When you look at a silicate, your pH is anywhere between 12 and, the upper 13s, middle 13s. Right? I've seen 12.4 up to 13.2. Again, we can use that in the situations we described. Colloidal silicas are below 10.7. Most of them are in a pH of like 8 to 9. You can even get colloidal silicas in a pH of 3.4. That's for very specific situations, but you can get acidic colloidal silicas. Silica does not like the high pHs. Hence the reason we have alkali-silica reactivity. So if we use colloidal silica at a pH of, let's say, 9, instead of a silicate for, let's say, hospitals, then you're not creating the same environment. You don't have the same amount of sodium that will drive the moisture up, that'll create that hydrolysis. Now you have a much more stable environment. Don't need to use as much product, or excuse me, I apologize. I meant to say that differently. I was trying to say it all classy. You might need to use a little bit more product, and it might be a little bit more expensive than the silicate. But you're going to have a much longer term positive impact. It's like I had to have a discussion with my team yesterday about investing in social media versus search engine optimization. Right? And this is something I often think that you have to consider too, for your podcast. Social media is amazing because it is a low barrier to entry when it comes to finances, and you can see the impact almost immediately. Right? You'll see the engagements, the comments, the shares, right? The numbers, you'll see like a spike in the chart. Search engine with social media, it's short-lived.
Mm-hmm.
2 days later, it's gone. Maybe even 30 minutes later, it's gone. There's no lasting effects. And if you do it the wrong way, it can also have a negative impact. Like for me, if I ever share any of the wildfire videos on LinkedIn, my numbers drop.
Huh.
I think it's hugely important, but short term, it did nothing for me. Long term, I had to work really hard to get those numbers back up, right? With sodium silicates, it's the same thing. Short term, it helps for flooring issues, right? You know, reduce the water migration, moisture. But long term, it doesn't help us much. It hurts us. With colloidal silica, just like SEO for search engine optimization, costs a lot more money. Initial investment is very high. Then you need to do some advertising, and it takes like 90 days to even see a positive impact with search engine optimization. But even after those 90 days, the value added performance, it just compounds. So I personally would rather use colloidal silica in search engine optimization than sodium silicates or potassium silicates in social media to grow our business and to treat a concrete floor that would receive resilient flooring. And that's me personally. I'm not recommending anything for the industry. I know there are people that swear by a certain technology, and God bless them. But I'm also the lead, or the what is it called? The expert witness that has to come in and be part of these challenges, these mediations, and I hate to use the word, but lawsuits. And I've been doing that for the last decade and a half.
Mm-hmm.
So, silicas, going back. I had notes, and we just deviated from them.
We always do. That's what makes this fun. Is the ASTM that you were working on, is that out?
It is
the
definitely
standard
out as something called a WK, which is a working draft.
Okay.
WK 80609. No, that's my old zip code.
Yeah, we had this trouble last time.
Oh, don't you say that. No, we didn't. No, we didn't. It's WK 60809. And I can show it right now.
Yeah, because I'm having a hard time finding it on the ASTM website.
Oh, whatever. Just look up WK 60809. Are you an ASTM member?
No.
That's why.
Oh.
So
I gotta
we've
join.
been working on this for 6 years.
I'll join right now.
What's that?
I'll join right now.
ASTM, people often make fun of it that, if we start a new ASTM, my grandchildren won't see it. And Nano-Shevitz is that rude. Screw those people for saying something and assuming that creating a legally binding standard or practice or certification process is an overnight thing. Shame on them. And especially for colloidal silica, which, Nano-Shevitz, it looks like an admixture, but it acts like a supplementary cementitious material.
Yep.
Like, I remember when we were first trying to get this into the industry back in I think it was like 2006, 2007, I was trying to teach people how to use colloidal silica or do an equivalent replacement of the surface area that you get from Class F fly ash with the surface area that colloidal silica. And I'm trying to teach this to batchmen. And they had no clue what I was freaking talking about, which I don't blame them. All right, let's see. Uh-oh. Hey, Tom. All right, let me open this up. I'm doing a podcast right now, just to let you know, buddy. Okay. Give me 2 more seconds here. So where we are at the tail end of finishing up the ASTM for colloidal silica. It's taken a long time to get the group together. We needed the right amount of manufacturers, distributors. So it was more than just starting it. It was also creating the book or the group. That group came together and we have been working our tails off. And the impasse that we have run into, there's a changing of the guard at ASTM. And what I mean is that you don't have the same people who created ASTM-C 618, 1240, 989, those other ASTMs for, supplementary materials for use in concrete, like silica fume, slag, and fly ash. You have different people, and because of that, they want different things. And, years ago, we convinced the industry that we had to go to, what's that called? Performance. And we need performance. And, our industry freaking generalizes everything. So we did just that. We generalized the concept, and now we want to see performance for everything. And that's what the impasse is. They want to see a performance section to this WK60809 to show that the colloidal silica does anything for the concrete, which I respect it. And if that's the little that we need to do to, how do I share my screen to get this passed, then that's what we're going to work on.
Down at the bottom.
Yeah, I got you. There it is. Okay, so here we are. This is the, this is the rationale, which goes over the history, the reason behind this, how we're going to separate it in the future. And this is where what we're working on right now. We've got the different types. Now we're going to the different classifications, and through the classifications or the classes, we'll create a testing protocol that looks at performance. And then here it goes over the growth over time. And then there's a much larger appendix to the rationale that like I said, we've been doing this for 7 years now. So it goes into a much deeper history and, the health aspects, the use in concrete and the benefits to it, some of the job sites, the need for an ASTM, and then the ballot history. This rationale will disappear once we publish the ASTM, but it's a great read nonetheless. And it's got some great references that we threw in there. The standard specification for colloidal silica use in concrete, when I created it, when we went from it looking like an ASTM for an admixture, the direction that we took was we wanted to use the ASTMs for silica fume, for fly ash, for slag as our rubric. So when you look at the title, it's standard specification for colloidal silica for use in concrete. It's identical to those other ASTMs there for silica fume, except for changing out the term colloidal silica. And in this, what we do is originally it was supposed to be a materials specification only. And what that means is first we had to define the colloidal silica, which I didn't want to create a definition that I thought would trump what was used here. What a wonderful definition. Aqueous dispersion of amorphous silica particles having a diameter between 1 and 100 nanometers and a solution pH no greater than 10.8. And it goes into a deeper discussion here of what a colloidal silica is and how it is separated from other technologies. But ultimately, the purpose of this was, and I'll shut up here in a second, Seth, this was a way for the entity that bought the colloidal silica for use in concrete to verify that what they ordered from the website or from the distributor or the manufacturer is what they received. And it was a way for the manufacturer to ensure that what they were sending from their warehouse is what was logistically transported to them through their gates at the end of the day. That's ultimately what it was supposed to be. Just almost like a uniformity check. First identify that we're actually using a colloidal silica. And here we have chemical requirements, physical requirements. And then we get into the test for those, but it was nothing more than that. The difference being now is we're starting to include performance tests to identify the difference between one colloidal silica and the next. And this is what a certificate of analysis would look like.
So the idea is colloidal silica going to be listed as an SCM in specifications?
Right now, yes, it falls under the ASTM committee for supplementary cementitious materials. And man, I always get confused with the numbers. I think it's 0924. Let me see. I believe it's at the beginning of this. Committee 09. I believe it's either 0923 or 24.
Mm-hmm.
Let me look that up. So ASTM 24 aggregates and pozzolanic materials. Yeah, so we're part of 0924, just like ASTMC 618. As a matter of fact, the guy who's in charge of ASTMC 618, he's like our group leader, mentor. It's Larry Sutter, who is another person you should have on your podcast because he's freaking amazing.
Cool. What's the time? What do you think the time frame is?
6 months to a year.
Yeah.
It's not easy to. It's easy to write this stuff. What's hard is you've got 20 people, or excuse me, 30 people now in our own subcommittee who have to agree to to agree to all this shtick. And then it's not just the subcommittee that we have to go through, which is the 0924, but then we have to go through the main committee. So it's constantly convincing people. And it's just a parliamentary process. And again, it's necessary because ultimately people are going to be held to the wire. This is going to have an effect on how people sell materials, buy materials, how it's governed back and forth. So it's important that we go through this laborious process, and it's a pain in the butt, but it's got to be done. So 6 months to a year. And if it takes longer, noch besser. I don't want it to, but if it does. The point is not that we get there. We don't want right now. We want it right.
Right. Yeah. Yeah. Meanwhile, there's folks that are using it, right, and getting the benefits of it, and not waiting for it to be standardized.
No, and I'm one of those. We operate our own colloidal silica company called Eddystone, and just like everybody else out there, we use ASTM-C 494 Type S for a special performance admixture as the way to give the industry a do no harm to their concrete. And it's a you want to talk about a process. I mean, that's a minimum 1 year process to certify that your product is not going to do any harm to the concrete. Great series of tests. And yeah, folks have been using that, the 494, as a way to get their colloidal silica product into the industry for a better part of a decade plus. I don't know how to shut that off. It's a good song.
There you go. Well, I think we're close to wrap it up. Is there anything else you wanted to hit on before we end the show today?
Is there anything else?
There's always something else, but just for today.
No. I recommended, there was something that the folks at Add 10 More Gallons did at the end of every show, which was ask you, what was your favorite concrete experience or your favorite concrete mix design? I want to follow that up. We didn't do case studies, but my favorite use of colloidal silica in concrete. I really love using it as a topical additive.
Yeah.
Whether it's, my favorite way to use it is damaged and deteriorated concrete. But there are so many freaking ways, and the leading thing, not only does it help the concrete, the value added performance, blah, 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 but it makes the job site so much flippin' safer and easier to manage. And if you're somebody in the industry that does, shotcrete repair and marine structures or bridge repair, pavement repair, there are too many companies out there that have colloidal silica technologies that can be used to enhance, rejuvenate deteriorated concrete. So, yeah, that's my favorite way to use it.
Yeah. Well, anecdotal stories I've heard from folks that are using it right now are very happy with it. If you're using it as an admixture, it's just easier for the guys to finish, and there's not a lot of it seems to be, I don't want to overuse the term self-consolidating, but that's how someone has described it to me.
I get the phrase, it's creamy and dreamy and easy to finish.
Right. Right. Versus someone sent me a note, or they wouldn't send me the submittal reviews, but an engineer was reviewing a mixed design and pointed out, I don't want to get you started on this, but pointed out that the Type 1L cement, the issues that they're seeing is the when they finish it, you're getting little pinholes in the finish. So they were warning the owner that this could happen with the Type 1L cement. But the person that shared that with me, I said, it's actually refreshing to see engineers, bring that to owners' attention, that there is that we're using a cement right now that's causing issues. So that was refreshing to hear that. But
that responsibility, man.
Yeah.
I love when engineers do that. I really do. It makes my heart warm. So no, that just warmed my heart.
Yeah. So this is a product that folks can consider to combat those kind of problems. So.
Oh, absolutely. Yeah. Absolutely.
Yep. All right, Jon, it's always fun as usual. Thank you for coming back on the show. Pleasure. Always loads and loads of information. I have a page full of notes. You talk faster than I can write, but I appreciate it. All right, folks, until next time, let's keep it concrete.
Talk to you later.
And that concludes another episode of the Concrete Logic Podcast. I hope you got some value out of that episode and learned a thing or two. If you did, visit our website, concretelogicpodcast.com. Click on the show support tab and learn how you could be listed as a producer of an episode. Again, that's concretelogicpodcast.com. Click on show support tab to learn how you can support the show. And as always, Mike Dunton will take us out.
Couple hours before the sun comes up. Open up the side, put some diesel in the lights, and wait till the trucks roll up. Yeah, this ain't how most folks live their lives, dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5s, we're out here changing these skylines with wood, iron, and mud. We work hard for $1, give thanks to the Lord above. Never make a man do something you can't prove. Hard work calls for a drink or two. Expect more, it's written in our blood. With wood, working hard to get that job done with wood, iron, and mud. We work hard for $1, give thanks to the Lord above. The color of our collars ain't white or blue. We're all gray collar through and through. Expect more, it's written in our blood. With wood, iron, and mud. Something you can't prove.